So I hope everyone can see the screen here. Let me know if you can't. All right, so as Matteo said, I'm going to be talking about first passage percolation, and maybe this is on the surface a seemingly strange form for it, because first passage percolation has been one of the random growth models that has been largely untouched by the integrable probability community. It has kind of evaded a lot of the integrable techniques, and therefore has proved to be a difficult model to get very precise results for, even though we believe, for instance, in the planar case, that it should belong to the Carter-Priggi-Zhang KPZ universality class. But I hope that this talk might serve as an introduction to something that maybe could in the future open up to some integrable techniques that would allow us to get better results for FPP. Right, so, and without, should go without saying, at any point, feel free to interrupt me, ask questions. I want this to be as followable as possible. So let me introduce the model. So this is FPP at first passage percolation on the integer lattice ZD. So what are the basic structures that we need? So first, we're going to introduce a family of random variables, which I call tau E. And here E stands for an edge in the integer lattice. And then the collection of edges, I'm denoting E of ZD. And these are just i.i.d. non-negative random variables. So these are called the edge weights. And with these edge weights, we can define for any path gamma. So imagine a nearest neighbor path in ZD. We can define for this path a passage time, which I call T of gamma, and that's just by that's obtained just by summing the weights along the path gamma. So I look at my edge weights tau E, I look at my path, and I add the edge weights along the path. And so this might be called the passage time for the path. Okay. And then once I have a passage time for every path, I can define a passage time between any 2 points. So let's say X and Y are 2 points in ZD. And I'll just define the passage time to be the infimum over all paths gamma, which go between X and Y, all nearest neighbor paths. And I just take the best one, which gets me there the fastest. So if I called T of gamma the passage time, then the T of XY would be called the first passage time. So I'm taking the shortest route with respect to these tau E's. Okay. And what we could be interested in for this passage time quantity, this T of XY, is what happens when X and Y are very far apart? What kinds of asymptotics does this T function display? So just to give ourselves a direction in which to send things to infinity, let me define E1. And this is just going to be the first standard basis vector. So this is just moving in the horizontal direction. And this is typical in the FPP world. We kind of focus on just this E1 direction. And then the fundamental result that gets the ball rolling is that if I look at the passage time between the origin 0 and n units in this horizontal direction, well, we should think of that a typical path between 0 and any 1 has order n edges. So if we divide by n, then maybe we can recover some kind of law of large numbers. And indeed, that's the case. So there exists a constant mu. And this convergence holds in probability as n tends to infinity. And this is without any assumptions. Oops. Erase this. This is without any assumptions on the edge weight distribution other than non-negativity. You can get almost sure with a certain moment assumption. I'm not going to focus on that in this talk. I'm going to try to keep things as general as possible. And this mu, this is called the time constant. So it gives us the rate of growth of this T function in a particular direction, the E1 direction. And just as a bit of culture, I'll mention that this result is due to the subadditive ergodic theorem. And these ergodic theorems kind of play a role in random growth models getting these first order asymptotics. And in this case, we're using the stub additive ergodic theorem because we're looking at first passage times. Okay. So any questions about just this preliminary definition and first result? So this is called the time constant, this mu. And we're going to be interested in actually what we can glean from this time constant via expressing it in a variational formula, which we'll get to.
So in case our random variables have some simple distribution, so can we explicitly express mu?
Yes. So this is a compelling problem, and in a frustrating state of affairs, the answer is no. So there is no known distribution for the taus for which we know exactly what this time constant is. So this is maybe an interesting question. Maybe some would regard it as less important because getting the explicit constant, you could estimate it numerically and you're not sure what to do with that information. But it would be more important to study the techniques that get you there. So if you had a method for determining an explicit formula for the constant, then probably that formula or that method would be useful in all these other sorts of questions that I'll kind of mention below, and many more in the first passage model that I won't talk about. But yes, this is a great question. At present, we have no way of determining mu for any known distribution, any fixed distribution. Other questions? Okay, and again, feel free to interrupt me anytime. So our interest in this talk is in geodesics. So these are the paths that achieve the infimum that we see above. So I'm going to typically use the notation gamma n. So gamma n is going to be some path between 0 and any 1. And we'll say it's a geodesic if T of gamma n is equal to T of 0, any 1. So the passage time between 0 and any 1. Okay. And there are all sorts of questions you could ask about geodesics, the first of which, the most basic of which, is just, do they exist? Because I have an infimum, and there potentially is a chance that maybe I take longer and longer paths that achieve a better and better first passage time, so there's no path that actually achieves the infimum. Now this seems a bit strange because you think that, well, long paths have high passage time. Indeed, this intuition in most cases will play out correctly, so the answer is yes. And this is under some assumptions. So this is at least if f of 0, so here I'm writing f, this is again common notation, but for those of you who are unacquainted, f is the cumulative distribution function for the tau e's. So these tau e's have cumulative distribution function we denote by f, and the minimum value that the tau e's could possibly take, 0, if that has an atom at 0, then we would want that atom is not a critical one. So that is, if I say this is the critical probability, PC of ZD, for percolation, Bernoulli percolation, then as long as the atom at 0 does not have that critical probability, then in fact geodesics do exist. Also, it's known that geodesics exist if T equals 2, so even at criticality. And I think that the general expectation that it should exist in all dimensions. We shouldn't have any problems at criticality. It's just we don't know how to show it. And this is kind of a long-standing, curious question. So geodesics do exist. We can talk about it. So the next question that you might ask is, what about their length? How long are geodesics? So just to give us a preliminary sense, to match some intuition. So what is known is that the length of gamma n, so again, I'm thinking of gamma n as a geodesic between 0 and any 1, is of order n. So this is a result of Keston. And I'm going to cite kind of implicitly here his book from '86, which is a wonderful resource if you're interested in FPP. It's kind of still a go-to for any specific FPP fact you want to know. But you could ask a finer question once you know that, well, geodesics do indeed have order n length. And again, I'll specify that this is if f of 0 is less than the critical probability. If f of 0 is greater than the critical probability, then you could imagine that there's an infinite cluster of zeros. So geodesics could just wander around in this infinite cluster and become very long. But as long as we're below this in the more standard case of subcriticality, this doesn't play a concern, and all geodesics have to be order n length. But as I mentioned here just a second ago, there's a finer question, and this is as old as FPP itself. So that is, it was asked by Hammersley and Welsh in '65. This was the paper that they originally introduced FPP in. And the question was, if I take the length of gamma n to divide by n, do I have a law of large numbers for this? So does this converge to some deterministic constant? And they actually argued something that is really simple, but it seems quite powerful. It gives you quite a strong result for nothing, is that if you replace tau e, the edge weight tau e, by tau e plus h. So here what I mean is take every edge weight and uniformly across all of them, just add a constant h, a positive constant h. So if you replace all the tau e's by tau e plus h, then this convergence holds. So that is, this question mark can be replaced by a deterministic constant. And this holds for all but potentially countably many h. And we don't know which h it could potentially fail for, so that's kind of the mystery of the whole thing. And the set of h for which it would fail does depend on the edge weight distribution of tau e. So this is kind of a sense that most of the time in a generic case, we should expect that geodesic lengths do converge on a linear scale. But still to this day, this has been the only method that has produced a positive answer to this question. And other than that, there's been no way of proving that geodesic lengths converge. So this still is a very interesting question. But the last one that I want to get to, and this is the one that kind of originally started my interest in these sorts of problems, is there a limiting empirical measure? So let me say what I mean by this. So let's define for a path gamma an empirical measure associated to that path, which is just defined as a sum of atoms. So I'm going to divide just to normalize here by the length gamma. So you sum over the edges of the path, and you look, what is the edge weight at that edge, tau e, and then I'm just going to put a Dirac delta mass associated for that edge and add them all up, and then divide by the length of the path to get a proper probability measure. So this gives us some empirical measure of the edge weights that are observed along a particular path. And the question is, if gamma n belongs to the geodesic set, so here I'm allowing for possibly non-unique geodesics. But let's say gamma n is a geodesic between 0 and NE1. And the question is, does nu hat gamma n have some weak limit? Again, I want a deterministic weak limit. So this was a question that was asked by Hoffman a few years ago. And there's been no positive answer to this question. So this is the kind of thing that we're going to be asking. Now, just to get ourselves acquainted with this notation a bit more, let me just give an example of how we might write something in this notation. So let's say I want to express T of gamma with respect to these empirical measures. Well, if I divide T of gamma by the length of gamma, then what is that? Well, that's just the mean of these empirical measures, because I've divided by this appropriate factor. And so what I'm left with is just the average of all the tau e's. So that is, I integrate the function t against the measure nu gamma hat dt. And let me give this kind of an abbreviated notation that I'll use henceforth, which is just t integrated against nu gamma in this inner product kind of notation. Okay. And so to kind of expand what this formula does for us? Well, it shows us that, let's say that I had a positive answer to this empirical measure question. So let's say that nu hat gamma n did have some weak limit, which we'll call nu hat, which is deterministic. Well, what would this imply? This would imply that, well, t of gamma n divided by the length of gamma n, which we just said can be expressed in this inner product notation. So that is, I'm using the identity function t as a test function. Well, if I have a weak limit, then we could say that this test function integration converges. And so this would have to converge to the test function integrated against our limit. Now, yes, there are some concerns here with maybe the test function here isn't bounded, it is continuous, but it's not bounded. So a priori, the weak convergence definition doesn't immediately tell us this, but ignoring that technical detail, just imagine that we kind of did have a bounded function, then this weak convergence would give us this fact. But again, if t of gamma n is a geodesic between 0 and any 1, what would that tell us? That would tell us that t of gamma n divided by n converges to our time constant mu. So now we have these two facts. So if we put them together, we would see that the length of gamma n divided by n converges to mu divided by t integrated against nu hat. So this is to say, if we had a positive answer for this empirical measure question, then we would have a positive answer for this length question. That is, if I know what the limiting empirical measure is, that is this nu hat, then I can write down an expression for the limiting length. So in some sense, we've asked a stronger question. Now, we should suspect that maybe sometimes the empirical measure doesn't converge, but the length does, because we've asked a stronger question. But at least this gives us a new route to answering this Hammersley-Welch question here that I asked before. If I can show that the empirical measure converges by some new method, then this would actually give us a backdoor into the Hammersley-Welch problem. Okay, so these are all the questions that we're interested in. And let me mention, just to give a little bit of motivation, what are some of the difficulties that we run into when you try to apply kind of some of the standard techniques? The main difficulty summed up, I would say, is that things are sensitive to perturbations. So what I mean by this is, imagine you perturb the edge weights just a little, or maybe you just perturb a single edge weight by just a little. Then the geodesic path might completely change, because a geodesic is just an optimizer. And if I perturb it, maybe if it just perturbs over a little, then there's some near optimizer that now becomes the optimizer. And the geodesic path could have nothing to do or nothing to look like with what it was before. So all of these geodesic questions are sensitive to perturbations in the edge weights. And so kind of your standard concentration inequalities, more classical techniques, they break down a lot of the time when you're asking questions about geodesics. All right, so before I kind of go on and introduce the methods we'll be using to explore these questions, I'll pause for questions. And if anybody wants to ask anything, please do so.
Of course, one can ask more refined questions about the geodesic. For example, we have the geodesic from 0 to this NE1.
Mm-hmm.
One can ask, for example, how much the geodesic gets far apart from the straight line connecting 0 to E1.
Right, precisely. So this is another very important question. If you believe in KPZ universality, at least when d equals 2 here, then the answer to that question should be of order n to the 2/3. So this is getting back to the 1/3, 2/3 exponents in the KPZ class. Now we're nowhere near close to showing that in the FPP case, but for certain LPP, last passage percolation models, this is known, certain exactly solvable or integrable models. And I should mention on that note that related questions to the ones I've just mentioned here regarding empirical measures are currently being worked on by Alan Fly and Ling-Fu Zhan. And I've touched base with them, and their paper should be out in the not too distant future. But they should have a very different approach to these questions for a very specific model, which is a bit different direction than what I've given here, because I've not made really any assumptions on the edge weights. But these two works might complement each other very nicely, especially if we're trying to answer some of these questions with integral techniques and get further information that could be generalized in some sense. Other questions? So I want to begin this is going down the route of proving something, although I haven't told you exactly what I'm going to prove. So let me emphasize just a change in perspective of how we're going to ask these questions, and also what the underlying model is expressed as. And then once we've changed our perspective in a simple but I think natural way, then we can actually get a lot of mileage for not much work. And my perspective change has two components. So the first of which is, instead of considering the new hat gamma n, I'm just going to consider new gamma n. So I'm going to omit the hat here. And all that does is it changes the normalizing factor. So instead of dividing by the length of gamma n, I'm just going to divide by n. But I'm still going to sum over all the edges of gamma n delta tau e. So I still have some linear combination of Dirac delta masses. I'm just normalizing so that it's not a proper probability measure anymore. But for instance, I could express now the length of gamma n divided by n. Well, now that would be the test function 1 integrated against this measure, just to familiarize ourselves with this notation. So all that happens there is that I have omitted the hat here, and therefore gotten a different normalizing factor. That's all that the notation means. So that's our first change. Our second change is that I'm going to view the edge weights as given to me in a different way. So that is, I could just imagine that my edge weights are supported on some probability space, and they're just handed down to me. Well, instead, I'm going to view them as a function of a different family of random variables. So here I'm going to use uniform random variables. So now these are i.i.d. uniform 0, 1 valued random variables. And this tau function maps the unit interval to the non-negative numbers. And all that we need to assume is that this is a measurable map. So in the usual Lebesgue sense. So this actually doesn't pose any loss of generality, because, for instance, one nice choice I could make for tau is the inverse CDF. So that is, if I was using the notation from before, the function f inverse. So if you take a general random variable and you consider its inverse CDF, and you apply it to an i.i.d. uniform random variable, then that actually returns the random variable with the right distribution. So this is just kind of a general fact, a nice exercise. And we're actually going to exploit this fact just to have a different representation for what the edge weights are. So now they're no longer just given to us as tau e's, they're instead a map of these ue's, and the ue's are given to us. So this might be just viewed as a coupling device, where I can kind of couple together edge weights for different distributions, but we're actually going to use it a bit more strongly than that. And I'm actually going to use it so strongly that I'm going to completely convert the question about these nus into questions about empirical measures with respect to these ue's. So to define the notation there, I'm going to use the analogous notation, except I'm going to change nu to sigma. So now sigma gamma n is 1 over n. And then I take the same linear combination, but now with respect to the ue's. So now I have an empirical measure associated with these uniform random variables. And I can recover the empirical measure for the original edge weights by pushing this measure forward by the map tau. So that is nu gamma n is the push forward of sigma gamma n under the map tau. So I'll write this notation as, let's use nu gamma n is tau star sigma gamma n. Again, just to make sure we're all clear, what this means is that if I want to integrate the test function f against nu gamma n, that's the same as integrating the test function composed with the map tau, pre-composed that is, against sigma gamma n. Okay, so I can go back and forth. And again, I've omitted, use the highlighter here. I've omitted the hat here to demonstrate that we have a different normalizing factor. Okay, so any questions on the definitions? Okay, so I've really done nothing, but let's actually see what we can get out of this. So let's again reconsider the quantity t0 and e1, so the passage time between 0 and any 1. And recall that if I divide by n, send n to infinity, this converges, at least in some sense, to the time constant mu. But I defined this t as an infimum. Namely, it was the infimum over all paths gamma n, which go from 0 to any 1 of the passage time, t of gamma n. And here I'll just carry the factor n through. Okay. Now let me give this set a name. So I'm going to define Rn. So this is not actually going to be exactly this set of paths, but it's going to be the empirical measures associated with the paths. And we'll see why I do this in a moment. So let me define Rn to be the set of sigma gamma n, where gamma n is any nearest neighbor path between 0 and any 1. And the reason now I've done this is that I can re-express this variational expression for t by saying, well, let me take sigma n in Rn, and now rewriting this in our inner product notation, this is just tau sigma n. And here the main advantage that we've given ourselves, technically speaking, is that now these are measures on the unit interval, no longer on the half line, on the non-negative numbers. The key distinction being that this is now compact. And so I could take, for instance, a sequence of these sigma n's that are associated to geodesics. So let me say I have a sequence sigma n, and then along some subsequence, let's call it sigma nk, this converges weakly to some abstract measure on 0, 1, let's call it sigma infinity. So I'm using the fact that the space of probability, or the space of, well, finite measures of a given mass on a compact space is itself compact. So in particular, it's sequentially compact. So for any sequence of measures on 0, 1, I have a convergent subsequence. That's what I've done right here. Okay. And now, again, this is weak convergence. So again, ignoring the technical detail that tau is just measurable, but let's assume that, say that it was bounded and continuous, then what this weak convergence would give us is that these tau integrated against sigma n's, these will just converge to tau integrated against sigma infinity. So these will converge to that. So what have we expressed here? Well, I have the time constant mu, and it's now expressed as the integral of tau against some abstract measure. This sigma infinity was obtained out of a weak sublimit, a weak subsequence limit of empirical measures associated to geodesics. But the fact that I used geodesics was just to get this equality. If I had used any other sequence of paths, I could have again appealed to this subsequence and then gotten some convergence to some sigma infinity. But because I didn't use geodesics, the limit would have been strictly greater, or at least as large, not necessarily strictly. But all of this is to argue that really what I have here is a variational formula, that this mu can be expressed as the infimum over all such subsequential limits. So now here, let me define in a more precise way. So this R infinity is the set of all possible subsequential limits of these Rn's. So what do I mean by that? So let's say this is the set of all finite measures sigma on 0, 1, such that the lim of the distance, so here I'm saying I'm using the Wasserstein metric, but you could use your other favorite metric on measures. Let's say the distance between sigma and the set Rn has a lim of 0. So there is some subsequence of empirical measures sigma that converge to this sigma infinity. Let me keep writing the sigma infinity, just to emphasize that we're sending things to infinity. So I've written here a variational formula in terms of this abstract set. I don't have a nice description of it at present, but at least I have a variational formula. And in order for that variational formula to be useful, I need to know the following thing. This is kind of the first major theorem we'll talk about. And it's that there exists a set R, a deterministic set R, such that this R infinity set equals that set R with probability 1. And this is merely, although the technical details are actually quite complicated, but in principle, this is just a consequence of 0-1 law. So in principle by the Kolmogorov 0-1 law. So you should be convinced pretty easily that the 0-1 law will tell me that for a specific measure, so if I pick my favorite finite measure on 0-1, then with probability either 0 or 1, that measure will belong to this R infinity set. And what I'm saying here in this theorem is stronger than that. That not only does that apply measure-wise for a specific fixed measure, but I'm saying there's actually a collection of measures such that simultaneously, with probability 1, all of them belong or don't belong to this set R infinity. This R infinity has an almost sure value.
Erik, there is somebody want to ask a question?
Yes, please.
Hey, Erik, what is W of sigma infinity comma Rn again?
Yes, so this W, I'm just using it to denote Wasserstein distance. But you could imagine any other well-behaved metric, any metric that metrizes weak convergence. So what I mean by this is that the distance between this given measure sigma infinity that you want to test whether or not it's in R infinity, if there's a sequence of sigmas from the Rn's that get closer and closer to the sigma infinity, then you do belong to the set R infinity. So it's just a set of all finite measures on 0-1 that can be realized as a subsequential limit of things from these Rn sets. Does that answer your question, Arjun?
Yes, it does. Thanks.
Yeah. Any other questions?
So is this being done omega by omega, or are you considering the random collection of measures that'll result in the geodesics, like the law of the measures that push forward to geodesics?
So if I'm understanding your question correctly, the answer is that when I write R infinity, I am doing it omega by omega. So I'm taking a fixed realization of the UEs and then considering what this resulting R infinity set is. And then the assertion is that there's a probability 1 set of omegas such that R infinity takes a specific value set-wise.
Okay, thanks.
So this variational formula now can be rewritten without this R infinity here. So let me That's the whole point. So we have a deterministic set now that the variational formula is over. And with that, we can do quite a bit. So let me extrapolate on that a bit. So what is the consequence of this variational formula? Well, let's say that I took a fixed beginning measure or a fixed beginning function tau 0. So tau 0 is just some measurable function on 0, 1. And then I add a perturbation. So I add h times tau 1. So tau 1 is another measurable function. And then I'm looking at what's the time constant associated to this FPP model, where I'm using these as this is my push forward map. And I'm going to compare it to what's the time constant when I was just using tau 0. So again, here I'm using 0 and 1 just to indicate two different measurable functions. I'm not referring to any particular edges. Well, expressing this in our variational formula, let me express the first term as the infimum over sigma in R of, well, the relevant test function is tau naught plus h tau 1 integrated against sigma. And then for the second one, I'm actually going to choose a minimizer. Now, why can I do that? Well, the whole construction here was appealing to some subsequence that got me to this sigma infinity. And so in fact, not only do we have this variational formula, but the construction shows that minimizers exist. And I'll add the caveat that kind of has been pushed under the rug, but this is if f of 0 is not equal to the critical probability. Because recall that the critical case, we didn't actually know that geodesics do exist. And so we couldn't necessarily appeal to this sequence of empirical measures associated to geodesics. But assuming we're out of that kind of exceptional case, minimizers do exist to this variational formula. So let me pick one of those minimizers for this guy, this tau naught. So I'm going to subtract now tau naught integrated against, let me call that minimizer sigma naught. This is a minimizer for mu of tau naught. Well, given that I've written this as an infimum, now I can say, well, let me choose a particular value of sigma here. Let's choose sigma naught. And now when I choose sigma naught and subtract these two quantities, all that I'll get is just h times the integral tau 1 with respect to sigma naught. Okay, so just put sigma naught there. That gives you one possible candidate for the sigma in R. So I get here an upper bound. And then when you do the subtraction, you just get this quantity. So what have we actually demonstrated here? We've demonstrated that this function mu is concave. So recall what the one way of defining concave functions is that for any perturbation, I can have a bound of this type, an upper bound of this type, where here, this is expressing the subderivative. So we have a concave function and the minimizers of my variational formula lead to subderivatives. So what we should conclude actually is that if you have a point of differentiability, so here I kind of haven't defined what that necessarily means, because the domain of this mu is not so clear how it has a structure that you can differentiate on. But if mu is differentiable at tau, then we should imagine then there exists a unique minimizer. And what do we know that the minimizers correspond to? Well, the minimizers were exactly coming from, remember how before I wrote the infimum here, this guy came from a limit of empirical measures associated to geodesics. Well, if there's only one minimizer, then that means there's only one possible subsequence when I choose the sequence of geodesics. And so a unique minimizer will imply a unique limit for empirical measures. So this is great news, because now I have a concave function that everywhere it's differentiable in some sense to be made precise, but everywhere it's, quote, differentiable, there exists a unique limit for my empirical measures. That is, I have a positive answer to the question that I started with. And this is all good news to us because we know that concave functions are differentiable almost all the time. And let me make that a bit more precise. So just to review here, differentiable function theory, or convex function theory. So if my domain is R, then on what type of set am I differentiable or guaranteed to be differentiable? Well, off of a countable set. And this should ring some bells because we were talking about exceptional sets that were countable earlier on in this question about geodesic lengths. In fact, you can infer now this theorem of Hammersley and Welsh precisely from this fact, where here, again, I've tried to use kind of suggestive notation. I was perturbing by h. So when I perturbed by h, that was really using the perturbation function tau1 that's just the constant function 1. And here I was perturbing it by the factor h. So when I perturb by h, then I can get down here, this subderivative has to be unique. And when I'm integrating against 1, recall that 1 integrated against sigma gamma is just the length of gamma. Well, let me write gamma n, length of gamma n divided by n. So if there's a unique value for this inner product when I have the limit, that's showing me that I have only a unique limit for geodesic lengths. So you can infer the theorem of Hammersley and Welsh from this type of fact. So here I'm thinking of mu as just a convex function of h. But I could think of it as a convex function of other types of perturbations, not just one parameter families. So if my domain is finite dimensional, Rn, then we know that a convex function or concave function is differentiable almost everywhere in the sense of Lebesgue. Okay, so that's a slightly weaker conclusion than an off-accountable set, but it's still a pretty strong conclusion. And in fact, I can go to an infinite dimensional space, namely a Banach space, and then differentiability, although you have to define it maybe in a slightly different way than we're used to in calculus classes. It's called Gateau differentiability, but the conclusion still holds on a dense G delta subset. And I'll add the technical condition that you have to have a separable Banach space.
So there's a question by Evan Soren. So if Rn is a single measure or a set of measures?
So Rn it's a set of measures that are associated. These are the empirical measures associated to the paths gamma n, where gamma n is any path, the nearest neighbor path between 0 and any 1. So look at all the possible paths between 0 and any 1. Look at the associated empirical measures with respect to the UEs. And then you just take the collection of those, and that's Rn. And this R infinity set is all possible subsequential limits obtained from the Rns. Other questions? Yeah. Okay, great. So here, if we had this first level of differentiability kind of result for convex or concave functions, and we got a certain type of result, we got a geodesic length result, then actually if I apply these kind of upper level differentiability questions, these kind of black boxes of differentiability for concave or convex functions, then I can actually get results for empirical measures. So let me first express what you can do with the second level. Here I'll write theorem 2. So let me fix any P1 up to Pn that are non-negative that sum to 1. So just fix any probability vector. Then, here's the conclusion. For almost every vector T1 to Tn in Rn, where all the coordinates are positive, we have a positive answer for the empirical measure question. When the edge weights tau e are distributed according to the linear combination pi delta ti. So you fix any of your n favorite probabilities that add up to 1. Then the conclusion is there's a p-dependent set, but it's an almost sure set, an almost everywhere set of vectors T1 to Tn, such that if I linearly combine these probabilities with these possible values for the edge weights, then what results is an edge weight distribution that has limiting empirical measures, that has a unique limit of empirical measures associated to geodesics. So this would give us the first example to a positive answer to Hoffman's question. Does the result make sense? Please ask questions if it doesn't. So that's giving us an example of what we can do with the second layer of the second level of differentiability for concave functions.
So by empirical measure, you mean the measure with the hat?
Yes, exactly. So in fact, it would be, you actually have a stronger result that it converges even without the hat. So Sunshine, I should maybe be more precise. The i.e., there exists a unique limit nu hat, so such that nu hat gamma n converges weakly to nu hat for all sequences of geodesics between 0 and any 1. So you can take any sequence of geodesics, and then the associated empirical measures have to converge to this deterministic limit weakly. So this is telling us that at least for a generic, discrete, and finite probability distribution, where the edge weights take finitely many values, we do have a positive answer for this question. And it has come to us for free. I mean, there's a lot of technical details that I've swept under the rug, but I've not really hid any intuition that you need. And this all came from just representing the edge weights in a slightly different way. So with that, let me move on to this third level rather, of differentiability. And let's see what kind of mileage we can get out of that. So here's a kind of example that we can get, a kind of theorem we can get from this black box. So namely, I'm going to fix any measurable function tau naught. So this is just any, again, it's just a measurable function between the unit interval to the positive half line. Okay. Then there exists a dense G delta subset. So I have to tell you what it's a subset of in order for you to understand what dense means. So it depends on tau naught, but it's a dense G delta subset of the subset of the Banach space CK, where here CK is a set of K continuously differentiable functions between the unit interval. And well, in order to make a Banach space, you'd want here the real line here, but I can actually consider just the set of functions that take positive values. So here on the right here, I have the set of K continuously differentiable functions that map the unit interval to the positive numbers. And there's a dense G delta subset of those such that for every phi in this dense G delta subset, we again have a positive answer. So, to Hoffman question. When what? I perturb this tau naught function by one of the guys from the specific set. So when the edge weights tau e are distributed according to, well, take your original tau naught function, add this perturbation function phi, which is k times continuously differentiable, applied to a uniform random variable. So when this is the edge weight distribution, then I have a positive answer. So again, this statement holds that there exists a unique limit nu hat such that whenever I have a sequence of geodesics, the associated empirical measures do converge weakly to nu hat. So any questions about this theorem 3? This is coming more or less for free from this result here, which you can regard as just a black box. So now I have examples of discrete finite distributions. Here, this is giving me an example of a, well, potentially a continuous distribution. You can, by choice of the tau naught, note that you could make that continuous distribution have unbounded support. You could, for instance, have tau naught such that tau naught of E, say, has infinite mean. Or you could have any bounded moment assumption that you violate, because tau naught here is completely arbitrary. It's any measurable function you want. So I can give positive answers to Hoffman's question for kind of arbitrarily poorly behaved tau naughts, for arbitrarily poorly bounded edge weight distributions. And you can use these 3 different types of differentiability results in some different ways to get other types of examples. For instance, you can get discrete distributions that are not finitely supported but are infinitely supported. You can get discrete distributions that are supported on a dense subset of a countable dense subset of R, or rather the positive numbers. You can get continuous distributions that are k times differentiable with respect to their density. So you can do a lot with this. And here I've just tried to skim the surface and show you what you can get as more or less free output. But if you use just a little bit more effort, you can actually get examples with more specific features. So just to kind of summarize, all of this came from these 2 shifts in perspective, maybe the second of which is more the critical one. But once we had this variational formula, which holds for any tau, you don't need any assumptions other than measurability, then you can use the fact that it holds very generally to make all sorts of perturbations, because you don't have to restrict the domain of tau, or the domain of mu, sorry. And once you have this general concavity feature, then you can use these differentiability results to get you a lot of mileage out of the variational formula. And these are just 2 examples, and the paper should be out within the next week or so, and then you can see more. If you have questions or want to chat about it, please email me or ask further questions now. So thanks very much for your attention.
So thank you very much, Erik. So let's see if There are some questions. I think Promit is talking, but his microphone is off. Okay.
Can you hear me now?
Yeah.
Oh, I was just like, thank you very much for the very nice talk. And I have a question about like this, this second theorem that also it's applicable for the third theorem. So you have this age weight to be empirical, like distribution of over like n weights, and then this gamma, a new hat gamma n converges to new hat. But this new hat, do you have any like sort of description of new hat in terms of this weight, like this PIs or PIs or something like that?
Promit. So there was a problem with your microphone, probably. So there was some fry.
Yeah, so it was a little choppy, but I think I understood your question from it. So namely, you were trying to see whether you can say any properties of this new hat from knowing something about the original edge weight distribution, right?
Yeah, that's right.
The kind of the first answer you can give is that it's absolutely continuous with respect to the original edge weight distribution. That should kind of be more or less clear because, well, any possible edge weights that I observe, they have to come from the original edge weight distribution. Now, that's not necessarily an immediate proof of absolute continuity, but it kind of gives you the general idea. Beyond absolute continuity, you could then ask, well, you have some Radon-Nikodym derivative, and what are the, do you have any nice, bounded in L1 or bounded in LP rather, properties for this? It's not a question that I've explored. However, I will give a nod to a ongoing work that Christian Jigian, Xiao Shen, Wei-Kit Lam, and Michael Dameron are working on, where they do address some of these questions without the assumption of necessarily having convergence, but just take any arbitrary subsequence, and then they can give you some properties of that it has to obey with respect to the original edge weight distribution. So once that those results are put out, then I think it would complement nicely some of the things I've said here.
There are ways also through like this variational description, or there?
No. I mean, to my knowledge, it's not going through any type of methods that I show here. I can't speak exactly to what they do, but at least they're giving some nice analytical properties that you can glean.
Thank you.
Mm-hmm.
So there's a question by Xiao Shen. Maybe she wants to ask the question herself.
Yeah, so Xiao, what I mean is that so you consider the Banach space of k times continuously differentiable functions on the unit interval that are real valued. So that is a Banach space. And then restrict yourself to the subset of that Banach space where the functions have to be positive valued. Then that's the subset that appears here on the right. And I'm asserting the existence of a dense G delta subset of that subset. So it wouldn't make much sense if I just considered the original Banach space itself, where I had real valued functions, because then I could have negative weights, which I don't want. But if you restrict yourself to the positive valued functions, and this is now an open subset of that Banach space, and you could talk about a dense G delta subset with respect to that set. So it's kind of replacing the Banach space by the space you want. Does that answer your question?
So is there any explicit requirement on the value of k?
No, so K can be arbitrary. So K is fixed, but it can be anything you want.
Okay, thank you very much.
Yeah. So I mean, in some sense, I mean, K equals 0 is kind of actually the strongest result because this is the biggest set. But in kind of in principle, the black box could give you a different set for every K that you choose. But yeah, K is arbitrary.
So is what's important here just that this is a Banach space of measurable functions? Could you replace it with some other Banach space of non-negative measurable functions?
Yeah, you could. What is important though, that enables you to get convergence of the empirical measures, because there's kind of this hidden step of how did I jump from, in the first case, just getting convergence for the length off of this result to, in the second and third cases, getting convergence for the empirical measure. And the jump is given by, you have to choose a space of functions that is sufficiently, that all of the functions separate measures on 0, 1. So that is that, for instance, the continuous functions, obviously, if I have two different measures on the unit interval, there's some continuous function that has a different value when I use that as my test function. And here, although that's not true for discrete distributions, all that you need is for you to be able to separate discrete distributions. You don't need to separate all probability or all measures on 0, 1. You just need to separate those supported on a fixed set of points. So in that's why even in this theorem 2, having this almost everywhere set is sufficient, because you can differentiate in all the n directions, and that's telling you that really in all those n directions you have the same weight on the ti. So on the ith direction, if it's just differentiable in that direction, you know you have a uniform weight on the ti, the fixed weight it has to have. So if that's true in all directions, then there is one empirical measure that has to have a certain weight on ti.
Can you say anything about, say, the empirical distribution of the consecutive edge weight, something like that, or something more exotic than just a single edge weight with this method?
Right. Yeah. So this is an important question. Thank you, Duncan. At present, no. I mean, I'd like to be able to say something about the edge weights with respect to the whole environment, right? The environment with viewed from the geodesic. But I can't do that because I don't really have a nice statistic to measure in the same way that I have the time constant measuring the value of the geodesic, the passage time. So I needed some kind of statistic to create my variational formula out of. And if that statistic doesn't differentiate between different paths that you want to be able to differentiate, so that is, here I'm not differentiating between any two geodesics, but maybe I do want to be able to differentiate between, you know, what does a geodesic have with, as you say, maybe one geodesic has an empirical measure with respect to consecutive edge weights. That's one thing. And then a different geodesic has that same type of measure, but it's taking a different value, a completely different value. I don't have any law of large numbers to distinguish those two, because they look the same with respect to the time constant.
Okay. Thanks.
So would it be possible then just to work backwards and figure out what kind of statistic you would want to answer that question with these techniques?
Yeah, it's kind of an interesting line of thinking. I suppose you could. I guess the difficulty would be just constructing a statistic that you are guaranteed to get a law of large numbers for, and then have have all of these nice inputs that you can, kind of draw from classical FPP theory. Yeah, it's not something I've really honestly thought about terribly much, but certainly it's an important direction to at least give consideration to. So yeah, thank you everyone for the great questions.